Hey there, welcome everybody, warm welcome. Get yourselves ready with a notebook, grab a pencil or a pen. Anything you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem which is not from any AP Calculus exam in particular, that I know of anyways. This comes from a resource of practice exams, which I'll leave the description, the link rather, in the description of the video. They have some pretty great multiple choice questions, a lot of different versions of the same types of questions. So shout out to the University of Houston for having these seemingly random resources, but incredibly useful ones. Okay, so today I'm taking a little longer in the intro because I need to preface the fact that some of these questions that we're going to see in this 3-part series of FRQs is that the questions are considerably easier than they will be on the AP exam. Now, not all of them are much easier, but given that there will be Desmos graphing capabilities when there's a calculator required, that means you really should expect there to be some tough questions. You should not expect easy questions on the graphing portion. With a tool like Desmos at your side, how can you fail? So they can really make it tough. Okay, let's get started here. You can see that I have Desmos shared as well. We're going to be using Desmos a bit because these graphs intersect at points which can't really be found by hand. Listen, check, but that would be very efficient. Alright, so we're letting S be the region in the first quadrant. Oh, right. As usual, give yourself about 12 to 15 minutes. Shouldn't take that long, honestly, to try to do this problem yourself. And then you come on back. See how we did it here. Alright, so we have this region in the first quadrant which is bounded by these two graphs. Now you should know what these graphs look like, regardless of whether or not we have to use a graphing calculator. You should know that and the fact is that this equation here is the equation for something kind of like a bell curve. It has sort of like a hill to it, and its highest point, of course, is at x equals 0, y equals 1, and then we have this other graph, this other function, which is the quadratic, and it's 4x squared, so it's actually very steep. Yeah, it's a very steep graph. So in the first quadrant, that's only going to be this portion right here. Okay? We need to find the area of the region S. Now that's just going to be a simple integral from 0 to what? That's the question. Well, we want to go from 0 to something of top function minus bottom function. This is the part where a calculator comes in handy. We're not going to be doing the antiderivative of e to the negative x squared. Make sure you get in the habit of putting parentheses around your integrand because that's how Desmos expects you to put them. Let's find that intersection point by graphing e to the negative x squared minus 4x squared. Interesting how that turns into a parabola. There is our point of intersection, x equals 0.45154. So remember that when you want to see when two functions are equal to each other, just find out when their difference is 0, and that will perfectly tell you. Let's see, this is going to be 0.45. Did it round up? I should have paid attention to that. 452. Yeah, what am I doing? I rounded down extra. Okay, 0.452. And then we're going to evaluate this with the calculator as well. So I might as well use the exact answer from 0 to 0.4515, was it? Yeah. Let's get another digit on there just because. Parentheses, no, forget those guys. Okay, I'm getting an answer that rounds up to pretty much 0.300. So I'm not completely relying on Desmos to develop any of these equations. I had the setup, then I just need to include this x value and then plug the entire integral into Desmos. But I didn't rely on Desmos or a calculator to motivate how to represent the area. I didn't even need to graph it because I understand what the graphs look like, so I already know what's on top and what's on bottom. That saves me time. I mean, it uses more time for me to draw it and show you guys, but you understand what I mean. On the exam, if you were to sketch that out really quickly, without explaining it, just knowing it and sketching it out, then it would be very clear what the top function, what the bottom function is. Okay, let's look at part B. Find the volume, here we go, of the solid generated when the region S is rotated about the x-axis. Okay, so if we're rotating it around the x-axis, we have to ask ourselves, is that one of the boundary lines? This is not a boundary. Therefore, the slices, the cross-sectional slices, which I'll sort of sketch over again, like sort of exaggerate it. Bam. And let's make this three-dimensional. Like that. And so these slices are going to have an outer ring, and then they're going to have this inner ring, right? So each of our slices is going to look like this, a washer. Here's the x-axis of rotation. This is little r. Oops, went a little too far with little r. There's little r. Went a little too far again, but it's okay. Here's big R. And remember, the little r is just the distance from the axis of rotation to the red boundary, to the closer boundary. So that's just going to be the function for x squared. Whereas the big R is going to be the distance from the rotational axis, the x-axis, all the way up to the top boundary, the further boundary, and that's e to the negative x squared. So we want the area in between circles. That's just going to be pi big R squared minus little r squared. That's the same as pi big R squared minus pi little r squared. Big circle area minus little circle area. And so therefore the volume is just adding all these things up triumphantly, as the music sounds. 0.45154. And we're going to be careful about this. We're going to say e to the negative x squared squared. What is that? That's e to the negative 2x squared. It just multiplies the exponent by 2. Or you can just put e to the negative x squared and then square that. This is also valid. I'll show you that on Desmos, how it really doesn't matter. Minus 4x squared. Squared, again, you can put 16x to the fourth if you really want to. It's not going to change your answer. You're still going to have the correct answer. And this limit is the same because we're adding these washers up from 0 until that point where they meet, which is at the same spot from part A. Okay, so now that I think about it, we already almost have all of this in place. Let's square that. Let's square that. And let's slap a pi on it. There we go. There's our answer. Now I want to show you, remember that answer. It rounds up to 1.059. I want to show you that I could just multiply this exponent by 2. And it would give me the same thing, right? And I could also expand this to be 16x to the fourth, and it's still the same, 1.0585. Okay? So however you like to write it is okay, as long as it's still correct. I know that sounds It's kind of ridiculous to say it in that way. As long as it's still right, you can do it. As long as it's logically still correct, you can do it, and that's why it's going to come out still right. If we're being technical about it. So you can put 8.5, you can just round it to 1.059, that's also fine. Alright, we're making good progress. Like I said, these questions are a little bit easier than you would see. This one's actually on par with an AP style problem, I think. But again, with Desmos coming on this year's test, or Desmos capabilities, I would not expect an easy exam. Definitely would not expect an easy exam. You should never expect an easy exam. That's the whole point of studying. You expect something difficult, so you study and train really hard, and then when you have to do the real deal, not as difficult. Okay, the region S is the base of a solid now. Each cross-section perpendicular to the x-axis is an equilateral triangle. Find the volume of this solid. So I'm going to redraw the region because I have my washers there. Let's do something like this. And then something like this. Let's three-dimensionalize this bad boy. Let's stick out like that. Oops, what am I doing with this arrow, bro? There we go. And so we're going to have these triangles that are equilateral. So that means the length between these two curves, that's one of the sides of the triangle. The other sides stick outwards in this direction, like in the three-dimensional direction. See what I mean? And the bigger this gap is between the curves, the bigger those triangles are. You see what I mean? It's almost like they're triangular sort of points sort of sticking out at you almost. And they get smaller as the gap between these two functions gets smaller. So that looks kind of funky in that three-dimensional way. Let's draw them right side up. This is S, this is S, this is S. Or I could just say bam, bam, bam. So these are all 60-degree angles. If I split this down the middle, you should be familiar with this practice. Then this turns into S over 2. This stays S. And this would be S root 3 over 2. All right, so the area of one of these slices, which is an equilateral triangle, is going to be given by 1/2 base. The full base is S. Let's get that right. This full base, which is the gap between these two curves, that is S. And then times S root 3 over 2. Sometimes we move stuff around and just call this root 3 over 4 S squared. But remember, what is S? S is the gap between them. So this is e to the negative x squared minus 4x squared. Then we square it. Okay? It's not like when we were doing the washers where we had r squareds. We were finding the area of these circles. We're finding the area of these triangles, and the formula for that is root 3 over 4s squared, but the s, it represents the difference in their height, the distance between these two curves. So the top minus the bottom, and then we square it. This again is going from 0 to 0. How did I forget it already? 45154? Is it really an anagram? I didn't remember that. Yikes. I'm usually on top of those guys. Okay, anyways, volumes here. Let's go, we're not going to square these now. So this goes back to a 2. This goes back to 4. See how easy it is to change these things. And then we have to make sure that we have a square root of 3 or 4. That's Danish and probably other Germanic for over. Or 4. Or 4, technically. Okay, so this is 0.1298. Let's round that up to, that 9 gets knocked up to a 10, so we have 0.130, I think is appropriate. Ooh, did y'all catch that? I just caught it. This is not squared, buddy. There we are. Completely different answer. See that? 0.12 or 0.130 versus 0.104. All right. So gotta be careful on the inputs. The input makes all the difference. Be constantly checking. You should be constantly scanning. Like your subconscious should just be scanning your inputs at all times, just as a standard, just to make sure that you're doing things right. And even if you seem like a crazy person going back and forth checking your work, that's fine. Everyone can tend to go a little bit crazy on the AP exam, just to make sure that they're plugging in everything correctly. Okay, so this is 0.1037. We'll just call that 0.104. Seems good enough. Okay. And we shouldn't expect that much volume. If you're wondering why these are such small numbers, we shouldn't expect that much volume. Like I said, this is really steep, so where it cuts through the function, in fact, let's take a look at these two graphs. Y equals 4x squared. See, there's really not a lot of space in here. It's not even a 1/2 in dimension, so it's very, very small. The area of that region is like, well, I mean, we found it, right? It's like less than half. Yeah, 0.3. It's a very, very small area. Okay, well, as I said, you should expect AP problems to get tougher. I can't tell you for sure that they're going to, but I know that you're giving better tools. And if they give you better tools and expect to keep the test competitive, then logically you have to expect that the test is going to be more difficult and have more missing variables, for example, more parameters. So just keep in mind of the basics. Make sure that you understand how to set up the area. Make sure you understand how to set up the volume of a solid that's generated from a rotation. Make sure you understand how to represent your cross-sectional areas, because that's where you're going to be getting points along the way. You're going to get 1 point each time you plug in your final answer, or each time you get a final answer. But plugging stuff in along the way is really what carries your score. Okay. So use Desmos responsibly and get familiar with it if you are not already. It's a very simple, user-friendly tool. Even I could figure it out, and I'm not technologically inclined at all. Pretty much a monkey when it comes to that. But Desmos is easy enough to learn, so take some time to learn it. Watch some good YouTube videos about it. Dedicate a weekend or two. And hopefully your teacher is encouraging you to do the same and helping you guys do the same, which is get more competent with the technology and the tools at your disposal. Well, look, that's enough blab out of me, I think. Hope you learned something today, and I'll see you guys next time in the second part of this 3-video series of some FRQs from the University of Houston. See you next time in the void.